Hello and welcome to DATE2021. My name is Saber Nabavi and I will be presenting our paper on understanding power consumption and reliability of high bandwidth memory with voltage underscaling. To begin, I will give you the basic argument for this paper. We already know that DRAM has problems and one of them is bandwidth. So as a solution, HBM puts DRAM chips inside a package next to the computing devices. But HBM has to use the package's power budget. We use undervolting to reduce power without losing bandwidth. However, the new challenge is that if we push undervolting too far, it will cause some unwanted bit flips. So in this work, we try to understand how much power we can save, what are the types and rates of these bit flips, and how we can trade off among power, memory capacity, and reliability. We explore this using a Xilinx FPGA with two HBM stacks with a separate voltage rate for HBM. Our experiments show that there is a 19% voltage guard band for HBM. We can save power by a factor of 2.3x, and we provide a fault map to help users take advantage of undervolting. Here is the outline of the talk. I want to start by explaining why we need HBM. We know that DRAM has problems such as power, latency, and bandwidth, especially when it comes to data-intensive applications. There are two ways to tackle these problems. One of them is to replace DRAM with an emerging memory technology such as PCM or MRAM. But these technologies have their own limitations. The other method is to improve DRAM, which has resulted in the invention of reduced latency DRAM, graphics DDR, and low power DDR. This is the category that HBM falls into because it focuses on improving DRAM bandwidth. And because of that, HBM is already being used in high-end devices and of course the Summit supercomputer. The main idea behind HBM is to integrate stacks of DRAM chips into the computing package. Everything is connected using TSVs, microbumps, and the silicon interposer. The integration allows for 8 efficient memory channels that are 128 bits wide. The benefits are an order of magnitude higher bandwidth, a smaller form factor, and lower energy consumption. But the challenge is that HBM uses the package's power budget, so we need a power-saving technique that saves power without losing bandwidth. Undervolting is one such technique. The hardware that we use for our experiments is a Xilinx VCU128 evaluation board. There are 3 superlogic regions on this device that contain reconfigurable fabrics. Superlogic region number 0 is connected to the HBM stacks. Each stack has 16 AXI ports that the user can use for accessing HBM. Traffic from these ports are routed using switches to reach any of the 8 memory controllers in the stack. Each memory controller is in charge of 2 pseudo channels that work on their independent regions of the memory. So when considering the entire HBM, we have 2 stacks, 32 AXI ports, and their corresponding 32 pseudo channels. The idea behind undervolting is reducing supply voltage without reducing operating frequency. We can do this because manufacturers provide a default voltage above the minimum that the chip needs to operate. The difference is called voltage guard band. The benefit of undervolting is that we save power without losing bandwidth. The problem is that if undervolting is pushed beyond the guard band, some unwanted bit flips manifest themselves. But if our applications can tolerate a faulty memory, we can save more power. So in this work, we undervolt HBM, then we push it beyond the guard band and report power savings and the rate and types of bit flips. In the end, we show the possibility of a trade-off among memory capacity, power, and fault rate. The HBM supply voltage in our setup is driven by an onboard voltage regulator. We control this regulator from the host and change the supply voltage at 10 mV steps. We have 2 sets of experiments, one for measuring power and one for reliability assessment. For our power measurements, we change bandwidth utilization by enabling or disabling AXI ports. Then we change the supply voltage on each bandwidth and measure power consumption. We also measure idle power by disabling all AXI ports. As for reliability, we test the entire HBM to understand how it behaves during undervolting. We also test each pseudo channel to see how each of them reacts to undervolting. Our data patterns are either all 1s to detect 1 to 0 bit flips or all 0s to detect 0 to 1 bit flips. We know that active power of DRAM is proportional to the square of its supply voltage. Therefore, we are expecting similar power reduction with undervolting. The graph here confirms our expectations. In this graph, the y-axis shows power consumption normalized to the power consumption of HBM at maximum load at nominal voltage. The x-axis shows voltage, and we only include the representative bandwidth utilizations. In our experiments, 1.2 volts was the nominal voltage and 0.98 was the minimum voltage that HBM needed to work without any faults. We can get a 1.5x power saving by just working in this range. Pushing supply voltage further down to 0.85 will give us a 2.3x power saving. As you can see, the power saving is independent from bandwidth utilization since we are only changing voltage and not the frequency. Now, if we divide our power measurement numbers by V squared, we are left with what we call the active load capacitance. The unit for these values is farad per second. They show how much memory is being charged or discharged at every second. Since F and C sub L are constant at each bandwidth, we expect these values to remain the same. However, our measurements shown in this figure do not confirm this. This figure shows these values normalized to the maximum values at nominal voltage for each bandwidth. Before 0.98, these values are within 3% of what we expect, but after that, they start to drop. At 0.85, they are 14% lower than what they should be. This is explained by taking the manifestation of bit flips into account. As we push supply voltage lower than 0.98, some memory bits stop responding. Therefore, their capacitance is not charged or discharged. This results in a drop in alpha, as can be seen in this figure. Let's take a look at the general behavior of HBM stacks during undervolting. This figure shows the percent of each stack that is faulty at each voltage. We observed three supply voltage regions: guard band, unsafe, and failure. The guard band region starts at nominal 1.2 and ends at 0.98 with no faults. The unsafe region starts below guard band and extends to 0.81, which is on the edge of the crash point of HBM. In this region, the number of bit flips increases exponentially. Our HBM stacks fail at 0.80 and all the voltages below that. Our memory cannot work with these voltages, and the only way to recover it is by restarting it with nominal voltage. Now let's have a look at how each XC port and its corresponding pseudo-channel behaves during undervolting. We see three categories of variations. They are across HBM stacks, pseudo-channels, and data patterns. HBM0 has 13% lower fault rate than HBM1, even though they both have the same minimum and critical voltages. Some pseudo-channels are more sensitive than others. For example, pseudo-channels number 4 and 5 from HBM0 experience higher fault rate than others in the same stack. The first 1 to 0 bit flips show up at 0.97, while the first 0 to 1 bit flips show up at 0.96. The average rate of 0 to 1 bit flips is 21% higher than that of 1 to 0 bit flips. We know that if an application is intrinsically resilient to faults, it can benefit more from undervolting. Here we have a simple table that shows how much power we can save depending on what fault rate an application can tolerate and how much memory it needs. If an application cannot tolerate any faults, it can only push supply voltage down to 0.95 on 7 fault-free pseudo-channels and get its 1.6x power saving. A 2.3x power saving is possible if an application can tolerate more than 10% fault rate and does not need the entire HBM capacity. Thank you for joining me, and I hope you enjoyed this as much as I did.